Alright everyone, so now we are back again to the vectors problems part 2 and part 3. So let's start it. So in vector part 1 we found out that the angle A, which is all right here, the resultant angle turned out to be 86.970247888.9, aka 86.97 degrees. Now I made a little bit change over there. So the question is now that if the resultant angle is less than 86.98, then what should NASA do to bring it between 86.98 and 87 degrees? Should they increase the speed? So if you can see right the question here, sorry if I did not share it before. So if you can see the screen here, the question restates that if the resultant angle is less than 86.98, then what should NASA do to bring it between 86.98 and 87 degrees? So should they increase the speed? That's option A. Option B is should they add more fuel and recalculate everything and make changes? Or they should wait until the wind speed decreases within the next 5 minutes, or they should just postpone the launch. Now, I have provided a table right here which has time until launch in minutes and seconds, and then it later goes down to seconds, and wind speed forecast, which is every wind speed with respect to the time until launch in the unit of miles per hour. So now I thought that it's better to go for wait until the wind speed decreases within the next 5 minutes, so that it would give us more better angle over the resultant angle will be more than 86.98. Then now we go on to part 3. So it says if you decided to take option A, then recalculate what speed they should launch the rocket where launching angle is less than or equal to. So this is supposed to be is between, oops, 86.98 degrees and 87 degrees. And it does say that the wind speed will be the same as 13 miles per hour. Then if you said option B, after adding more fuel, what should they recalculate and or increase? So should they increase the speed or should they increase the angle? And if you chose option C, you should recalculate the resultant angle using t equal to 47 seconds from the forecast table, which is in row 6 right here. 47 seconds, which is given as 12.64 miles per hour. And it does say that you may need a calculator for this, and it could be beneficial if you use the work from part 1. And if you said option D, what is your reasoning behind it? So option D was postpone the launch. Why should you postpone the launch? And of course, you have to ask other questions like what would it cost for if you postpone the launch? What would change if you postpone the launch? So basically, if you said this, option D, you would say something like since we are under the backup radar, we can postpone the launch for 5 to 10 minutes, and then we can, I guess, wait more and then add more fuel if you want to. That could be some reason, and use more fuel while you are lifting up and off. That could be a good reasoning, probably. Then, if you said option B, after adding more fuel, which is right here, add more fuel, recalculate everything, and make the changes. So you just added more fuel. So what should they recalculate now? Should they and it asks for if they should increase the speed or the angle. So for this, I would say that if they increase the speed, it's going to help it, of course. so that when you're finding the resultant vector and the resultant angle, it's going to be very, very close to what we had for uh, it would be very, very close to what we have right here, 86.9702 blah blah blah. That one, it would be very, very close. So that's that. And if you said option A, then you have to recalculate what speed they should launch the rocket, where launching angle has to be between 86.98 degrees and 87 degrees. So the wind speed will be the same as 13 miles per hour. So of course you are going to use the things that you have done from part 1, and if you chose option C, then you are going to recalculate the resultant angle using t equal to 47 seconds. So which of course is going to be 13 miles rather than 13 miles per hour, it's going to be 12.64 miles per hour. And let's do that first, because that's I think that's the most best option you can ever see, or is cost efficient, I'll say. All right, let's let whiteboard load up. Okay, it's loaded, and so don't use that. So it's between 86.98 and 87 degrees. All right, so let's start again by drawing a sketch of it. That's that, and I made a mistake again, so I'll just use the ruler and create an angle of 87 degrees right here. All right, so this angle, let's choose green. This angle is 87 degrees. The wind speed now is become 12.64 miles per hour. And if you note, it's going in the same direction where it was coming from. So it's going eastwards. So it's going eastwards. And the rocket launch is going above, so it's northwards, and it's going at 25,000, I believe, miles per hour. So it's 25,000 miles per hour. All right, so we got this stuff in. Now, of course, from the problem that we did before, we created another line or vector, as we say, right from this point where 12.64 miles per hour ended at, which, and what we are trying to do is making a parallelogram. So this will help us to find out our resultant vector, aka I'll say for this case it would be resultant speed and your resultant angle. So this red line here is your resultant angle. I mean vector, I'll say for now. Then you have this becomes 12.64. If you see that this has become now a geometric shape, and which is a parallelogram. So we are going to use the properties of a parallelogram, and this would be 25,000 again here. This would be miles per hour, miles per hour. Now opposite angles in a parallelogram are equal, so this also becomes 87 degrees. Now we want to find the other two angles, but before we go ahead and do it, let us label out all of these things right here. So let's say this is A, this is B, this is C, and this is D. All right, now what we want to find out is angle D and angle B. If you notice, like I said before, it was 87, angle A equals to angle C because it's a parallelogram property in there. So now what will happen is angle D equals to angle B, but we want to find that only, right? So the sum of sides, not the sum of sides actually, it's sum of angles within a parallelogram equals to 360 degrees. And if we do 360 degrees minus 87 like this and divide it whole by 2, we get 93. So each angle right here, we just found 93 degrees for angle D and angle B. And of course, we did it in the last question as well, and the first part as well. So I could have just taken it, but it's better to show it again. All right, so now we can continue on finding the resultant angle and the resultant vector, or the resultant speed, I guess, in our case. All right, so since we have got all of our stuff in, now we're just going to calculate. So in triangle ABC, angle A is unknown right now. Angle B equals to 93 degrees. We'll just write out everything what we have. Angle C is unknown. What we have is side A equal to 25,000 miles per hour. What we have other thing is C, which is 12.64 miles per hour. And we don't have V, and that's what is resultant speed in our case right here, which is not necessary to be written right now, but it's fine. So what we are trying to find is first is B, which is a resultant speed, and resultant angle from the ground, which is angle A. All right, so let's start by finding the resultant speed. So to find resultant speed, we are going to use law of cosines. So it's going to be b squared equals to a squared plus c squared minus 2ac times cosine of angle B. Now b squared stays the same, or we can do this way, like this. A squared, which, what's a, that's 25,000 squared plus 12.64 squared minus 2 times 25,000 times 12.64 times the cosine of 93 degrees. That was angle B, B for beta. Now, if we get all of the stuff inside our calculator, we will get that B equals 25,000 point 664713042, which we can round it up as 25,000.66 miles per hour. Now, since we have got our B, side B, which is our resultant speed, we can now find resultant angle using law of sine. So it's going to be sine of A, because that's what we want to find, the angle A over A equals to sine of B, which is provided to us, over B. Sine of A over 25,000 equals sine of 93 over, oops, it was supposed to be this, so I'll just copy paste it. Best thing ever you can do, copy paste. Of course, not an exams, but it's good right here. So this is going to give us sine of A equals to 25,000 times sine of 93 over what we got before, and then we just do sine reverse. That gives us angle A of this whole thing. See, I'm just copy pasting a lot of stuff. That will give us 86.97, 107, 17225. So here's the thing now. We did not get it like between 86.98 and 87, right? So I believe that they should postpone the launch until the wind speed goes like to way less than 12.61 miles per hour. Because if we do that way, it's still going to give us somewhere around like 86.97 point, sorry, 86.9730 something. So for that reason, I say it's better to postpone the launch until it's way less than 12.61 miles per hour. So that's how it works. Hope this helps. Boom.